So in the previous class, we have covered a lot of things about arrays, and we solved some peculiar questions, some typical questions around that. So we saw some recent, like some new techniques like sliding window and two-pointer technique. And then regarding that, I have given a very interesting question. If you have gone through the assignment, please do that. So that'll help you to get through how do we use this two-pointer technique well, right? So please do that. So today we'll be starting with linked list. So before that, I forgot to mention you that how do we calculate the time complexity of the both of the functions, right? The merge sort and quick sort that we have discussed in the last class. So we'll try to discuss what exactly happens and how do we calculate the time complexity over there. Okay. So we'll start with quick sort. So I think quick sort is pretty clear. It's easier as well, but just for the sake of clarity, we don't want to get into the proof, but it'll be good if we just able to think it through intuitively or through a normal approach. Yeah. Anyone wants to try it out? What should be the time complexity and how we should calculate it? Anyone? Okay. I'll give a basic overview. So in quicksort, what were we doing was we were given a array and then we were finding the correct position of the pivot element, right? So we initially chose the pivot element as part of our algorithm as the array. And based on that, we have to figure out what is the right position for this pivot element. And we consider that this element is sorted, and we do apply quicksort on the left half, exclude the already sorted one, and apply quicksort on the right half. Okay, that was the basic algorithm we followed. So when we're talking of time complexity, we should always be concerned about what's the worst case scenario. Okay, so what bad can happen and what is the worst case scenario that can happen. So it can happen that when we are dividing it, what could be the worst case? So if we have seen, the first time user will not be able to know that why this is a bad time. So he will think of the time complexity, but I'm just reversing it. I'm using that to figure out the time complexity. Okay. So because we have seen if we divide into two halves that we are doing in merge sort, it performs better. But if you come across this thing in general, okay, the first step you landed into an array and someone gave you that, okay, what should be the worst case scenario? You might not be very sure, but once you find the time complexity in both of the cases, you'll be pretty sure that this is what it is. Yeah. So what is I'm saying is there are two cases, right? So either the quicksort algorithm that is running will divide our two arrays into equal subpartitions, right? So that is n by 2 and n by 2 each. Or there is another case wherein it just partitions as n minus 1 and 1, right? Like that means the pivot element that we chose is landing into the last position. That is, it's an already decreasingly sorted array and we're trying to sort it in increasing order. Okay. So in this case, the first time or the beginner ones will never be able to know like which one should be better. So for now, let's discuss the second case because the first case will be coming under that merge sort and will be explaining why it is better and how much better it is. So in this second case, what we're doing actually, so we were dividing a single array into two arrays. One is n minus 1, the rest is n. But this one, the second part here should not be included in the quick sort because it is already sorted. That position is already fixed. So we are only concerned with this half. So at each step, If this continues, that means if we are given a decreasing order array, then this step will continue, right? So we'll start with n, we'll go till n minus 1 in the next step, we'll go to n minus 2 in the next step, we go till n minus 3 in the next step, and so on. So how many steps will require to reach step number 1 or stop the quicksort function? What will be the number of steps this would be?
N into n minus 1 by 2, sum of n numbers.
No, I'm talking about only this step. What will be the number of steps we'll be needing to reach from n going down by 1 and 1 to 1?
N.
N.
Yes, it'll be n steps, right? Perfect. Now, we'll assume that we are doing this. So again, what we are doing, what was the crux of quicksort? The crux of the quicksort was this partition function, right? So partition function, what it was doing, if you remember, it was comparing the elements one by one and dividing the elements into two halves such that the left half is not sorted, but it is sorted relatively. That means in terms of the pivot, the left are smaller than the pivot, the right are greater than the pivot. So in that case, it can happen that it might land up in a scenario where it compares all of the elements every time. So the partition function in the worst case scenario can be a linear time complexity algorithm. So it can take an order of n at the worst case. It cannot go beyond that because it's just we're traversing through the element, through the array once. So what you can think of is like we have n steps, and at each step we are performing an order of n. So roughly we can figure it out that, okay, it should be an order of n squared solution in the worst case scenario. So this is the intuition behind this. Everyone got this? So we're not getting into mathematical proof, because for mathematical proof, we need to learn Master's theorem, and that will be a little bit mathematical. We need to learn a lot of things that will not be required for interviews and all. So this intuition would work. I hope everyone is fine with this. Or if time permits, maybe in the last class or so, when we are discussing only problems after the course is finished, I'll just give a basic overview of what Master's theorem is and how it should be used. Okay, everyone good? How it is order of n squared?
Yes.
Cool. So next comes the time complexity of merge sort. Okay, so we have merge sort here. So when we have merge sort, what exactly we are doing? So if you observe, we had an array of length n, but we are dividing equally into two parts at each step, right? That means at second step, we are dividing into n by 2 and n by 2. In the next step, we are dividing this n by 2 into n by 4, this into n by 4, this into two pieces of n by 4 as well, because the merge function behaves like that. We divide every time from the mid, and the merge function or the merge algorithm as part of the merge sort does these merging, right? These two sorted array merging, it does on its own. The next step, it will go till n by 8. It will go till n by 8, both of them. Similarly, this will get two sets of n by 8, and so on. So similarly, it will reach 1 in some cases. So what should be the number of computations or number of iterations to reach this level?
Log n.
Right, it will be log n, right? We have understood from the binary search that when we divide it into two halves, so if first is n, then n by 2, n by 4, n by 8, to reach 1, we'll have log n steps. So if you think about merge sort, what we're doing in merge sort. So in merge sort, we're not doing anything. So what we're doing is we are just dividing the whole array into two parts, and then we're passing that whole array or the mid as part of this merge function, right? So it will not seem that because we're not passing it here, but we are actually doing it from the lower side, right? So we do actually come here because we just consider the base case as the scenario wherein there is a single element in an array. If an array contains a single element, that is by default sorted. So there is no choice to think of that. So we start from bottom. So we go towards up. what we do actually, when we have this, at the bottom, we'll have how many arrays at the bottom of size 1?
Uh,
N, right?
Yes, it'll be n, right?
mhm.
So there
Yeah.
might be n or n minus 1, depends on the odd number or even number. So more or less, it'll be, we can consider that it has n, right? There will be n number of arrays. Okay, because the 1 can have occurred in some of the previous steps. So we can consider that as n here. So at each step, if you see what we're doing, we are merging this. So ignore that step. Think of this step here. Okay. So in this, what we're doing, we are merging n by 4, 2 n by 4s into n by 2 and 2 another n by 4s to n by 2, right? So what we're doing is we're merging 4 n by 4 arrays, right? To get 2 n by 2 arrays, right? Everyone clear till this step?
Yes.
Similarly, if we consider another level, we are merging 8 n by 8 array to form 4 n by 2 n by 4 arrays, right? Everyone clear?
Right.
So at each step, what we're doing is we are actually merging, or we are actually comparing n elements, right? So if you see here, we are comparing n elements. At this step, we are also comparing n elements, though not n at one go, but adding all of these two branches will add n elements, because we need to create a new array every time from this two partitioned array, right? So similarly, this will happen. So at each step, we have only one thing that is happening, that is the merge function. If you think of the recursive call, we're not doing anything, we're just dividing it, we're passing it to the new merge sort function that is calculating from the bottom, but the crux lies in the merge function. The merge merges the array and creates and backpropagates that to the top. So we had log n levels, and each step we are doing n operations, right? So each time we are, or each level, we are adding up all of this n elements to form the next step array. Okay, so it gives an intuition, and it actually performs that we have log n, and at each step we have n, so it performs in the time complexity of order of n log n. Okay, everyone clear?
Yes.
Cool. I think it was the time complexity of these two algorithms. Okay, shall we move forward, guys?
Sure.
So now our next topic starts, and that is linked list. So we'll see some more problems in arrays, but that will come as part of stacks and queues. So we'll discuss it over there. We'll also discuss heaps. So we'll discuss some more problems. Okay. So let's start with the discussion. What exactly is linked list? Anyone wants to introduce what a linked list is, why it is used, what are the advantages, what are the disadvantages?
So basically, it will have two data elements, like the value and what is the next element, and a
Okay.
reference to the next element.
Okay. Perfect. So what exactly is linked list? Like if someone tells you to define, what exactly is linked list? What we should tell?
List of elements or elements.
Sorry, your voice is not audible. Mantu, you're saying something?
No, I'm just saying that probably a set of elements where each element also provides a link to the subsequent element.
Exactly. So both of the definitions are almost same. It is that instead of the only value that we're having, we'll have some more information about the next element in the line. Okay. That's the linked list. So linked list is basically a collection of nodes, and each node comprises of two things. One is the value that it has, and one is the address or the reference to the next value it is pointing to. So it's basically forming a chain. Okay, that's the definition of linked list. Why it is used and what are the advantages of it?
Basically, when you don't know in advance, let's say the size
Mhm.
of the structure you need, right?
Okay,
That could be one.
but
Uh,
we have our Python list as dynamic, right? We don't need to initialize it with a particular size.
Internally, what does it use? Then I don't know about Python, so I'm asking.
Okay,
Like in other languages, it used arrays inside, from what I know.
okay. Anyone else?
So basically, insertion would be a lot easier in the sense like, if at all we need to add any element in between the list, then it would be
Right.
a lot easier because all
Perfect.
we need to do is we need to update the pointers. But in case of arrays, we have to shift all the subsequent elements, right? That means, let's say, if we want to add, if array has like 10 elements, if we want to add another element at fifth position, you
Right.
have to add element at fifth position, and you have to move whatever it is occupied earlier in the fifth to sixth, and sixth to seventh, and so on.
Perfect. That is one great advantage. The insertion time in case of linked list is very smooth or very fast, we can say, because here we don't need to have a contiguous memory location. So linked list and the list that Python provides are mostly the same, but the memory layout is different. Okay, the memory layout, as in the list that we use as Python, is a contiguous memory location, but the linked list is like separated out or discrete memory locations which are linked through the pointers. Okay, so for example, I could remember a best example I can think of is that, like, you go to a cinema hall with your friends and you don't have enough seat as sitting to be a single row, right? So what you do is you tell that, okay, you just remember one person's next where he's sitting, and through that you'll form a chain. So when the first person remembers the seat of the next and the second person remembers the seat of third, so on, they just remember the whole list there. So even if you don't sit together, you know where the other people are sitting. So that actually helps. For that reason, the insertion actually helps because we don't need to create a contiguous memory location again that we need to reallocate for list, shift the elements, create a vacancy, and put it there. But in linked list, we just create a node from the heap, change the pointers, and we're done. So insertion is very efficient. Perfect. Anyone else?
The same way deletion as well.
Yes, deletion also. So deletion also works same because in list we need to shift all of the elements. So it's not like you are given an array and someone told you to delete an element. Okay, so there are n number of elements. So someone told you, okay, you delete the second element here or the second index element. You just cannot delete it keeping it blank, right? What you need to do is you need to shift the other elements to this position. That will help in reducing the size as well. But in case of linked list, what you do is you just go and change this pointer to this. So we have deleted our previous element. So deletion is also efficient. Okay, these are some pros. And this is all possible because it is, or it has basically a non-contiguous memory layout. Okay, that you should remember. And what are the disadvantages, if any?
Lookup of the item in the list.
Right. Lookup or access it is
Yeah.
a problem because we don't have this index, right? We don't know uh, if the element at third is sitting at which index. So it is just known by the previous element. For that previous element, we need to get to the that's previous element. So basically, we need to start from the head of the linked list, and we'll have to traverse through to get a particular element. So that is a con. One is accessing. Anything else? So memory footprint wise, it also is a con because we need to store two structures in a single node, right? In arrays, we're just storing the values, But in linked list, we need to have an extra memory footprint for storing the references. So memory consumption is a bit more. What else? So mostly this. So mostly our performance. So now somebody can ask exactly what situation do we use a linked list and what situation do we use an array. So that exactly depends. If your algorithm or your situation requires constant insertion in the mid, you need to use that as a normal linked list. So suppose if you are writing a producer consumer for your web application, so suppose you are writing a messaging service, so you are using a consumer and producer over there. One, your service is producing the messages and they're put into a list, so we need to process them sequentially. So there is no position of like insert into a middle or removing a middle element. So in that case, you don't need to use a linked list because a simple list will do, because always there will be an append at the end. Even if in some cases, if you're using a list, it's better to use a linked list for append functionality. Is because when we consider a list, we consider the dynamic list, and dynamic list resizes itself every time it reaches a bound, right? So we have discussed this a little, like when we are given a list and that list is filled, like it's filled to its full. So obviously that is not full. So there are some pretty calculations. So it resizes itself. So in that case, what it need to do is you need to find a new contiguous memory location that is somewhat bigger than the previous location, and need to copy this previous element and need to insert that. So that is a bit challenging and that is a bit time consuming. So that again can be replaced by using a linked list where you can just search a node, single node value and link it to that. So that will do. Okay, so we just know about linked list. We just know about why it is used, where it should be used, and what are the advantages and disadvantages. So let us learn about some of the terminologies of linked list. So what we'll be using as part of our regular culture. So first is the head. So a linked list is a chain. So chain has a head, and the first node, we can say it as the head of the linked list, or we can create a pointer to point it to the first node. So the first node can be called the head, and this reference that we are pointing it to can be called as a head pointer. So obviously there is no concept of pointer in Java, but pointer in Python, but we are assuming that whenever we are talking of pointers, we are considering references, okay? As like Java. So Java doesn't have pointer either, so it is same. Next, we'll consider as a node. So node is basically this single structure which consists of two things. One is a value and one is an address. So each node will have two things. So as discussed, which have a value of its own and the address of its next pointer or the next memory location. For example, if this is at address 100 and this is at address 150, so this address will hold the number 150 here. So similarly, if this is at 150, that means this creates a virtual link to this position here. Next, the 150 will have its own value, and suppose the next location available is at 500. So it will consist of the address as 500 here. So basically this creates a point to this location. So each of this entity here is basically a node, okay? And suppose, for example, we have the last node here. So it's not pointing to anything. So we can have the last pointing to nothing, or we can see it as a null, right? Or none in Python. It is not pointing to anything, so we can make it as null. So the head is there, the node is there. So each individual entity is a node, but when this whole entity or this whole chain is taken into consideration, that means when we have a list of nodes connected. We have this, 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 and this. This is connected to this. This is connected to this. This structure is called a linked list. Okay. So we'll have to represent using another entity. So this structure is called a linked list. So we'll see that when we code, what exactly difference does it make and how do we know that? So we know about head pointer, we know about node now, we know about linked list, and we understood about the null or none. Perfect. Everyone clear till now?
Yes.
Okay, cool. So let's see some examples of how do we implement that. Okay, give me a minute. I'll open up my ID. Okay, so today's date, it's 19 or 20. Okay.
19.
So it's 19. Okay, we'll take a new file that is linked list.py. So we'll have two entities. So as of now, we don't have a single collection or something which the Python provides as a direct list or linked list implementation. Okay, so there are some queues implementation which internally uses a linked list, but as of now, we'll try to create our own custom data structure and how do we play around with it. So first of all, we'll have a class node. Okay, so when we are creating sort of our own custom data structure, so we'll use this class variable. I hope everyone is aware with object-oriented programming to a little extent. We'll not use much though, but the basic of why we are using it. Okay, so we have a class node here. So when we are defining any class, we need to provide a constructor. Okay, so constructor is basically the object creations engine. So whenever we call that node of this, it needs to create the object. It needs to pass through the constructor. So constructor is the object creation engine. So we need to define that. To define that, we have an init method. So whenever we call this, we are calling init internally. Okay, and whenever we are declaring a class and whenever we're defining any functions inside it, we have to make sure that the first argument itself is the self. So people coming from other languages like Java or C++, so this is exactly the instance of that class. So whenever I'm calling a node, so suppose I called node of 1, okay? So this instance will get represented by this self object here, okay? So this will make a little sense when we try to code it, but if you're aware, it's good, but if you're not, just bear with me a little while. So we'll have to have self here, and we need to have define two things, right? So because we need to have the data that is holding by the node and the reference to the next pointer. So we'll define data here, and we'll define the next here as none. So basically this data, that means what we should pass it here. So this self.data is the initiation. So in other languages, what we're doing is we need to define that, okay, these are the types, sorry, data is there and the next is there. And after that, in the constructor, we do this, but Python does not require that. We can directly define it using the constructor. So when we have this, we're telling that there is a data attribute in this class and there is a next attribute in this class object. So when we define it as part of this class, that means when the object is created, each object will be allocated 2 spaces for each of them. That is data and next. And this data is different from this data because this data is basically instantiation. So we need to pass in. So when we are creating, we need to pass the value, right? So when we are creating a node, at least it should have a value. Even if it is not pointing to anything else, it should have a value at least. So,
So sorry. So
yeah.
without knowing the type of data, how does it know how much to allocate?
So that's Python's interpreter, right? So everything is dynamic.
It's
So that
dynamic.
is
Okay.
the,
Okay.
so it's a
Just
beauty,
like
or you can,
JavaScript. Okay.
yes, exactly. So you can treat it as a beauty, or you can treat it as a curse, but it is what it is. So it is there. So we need to pass in this data. So when we want to create a node 1, that means we are creating a node which we are accepting that, okay, this should be initialized with the value of 1. So there are two ways to do that. If you are aware with object oriented, you can do that as you can initialize both of them as none and create another method to instantiate. Okay, maybe set data or something, and you give in an object and the data here, self.data equals to data here. You can do this way as well, but
Ravi, one question.
Sorry.
One question just.
Yeah.
You are writing bottom node 1, right?
Yes.
And in the init, you have self.data and both are none, right? Data should be something, right?
Yeah, that's what I'm telling. So this is another way of doing that. So if you are instantiating n equals to this node, you can do it like n dot set data as 1 as well. Okay. Got it?
Yeah.
So that's again a hassle. So that's why I prefer to pass it as part of the constructor. So we have to pass the data here. We initialize the data here. So instead of doing all of this, calling two methods, I'll just call a single method. That is 1 and 2 equals to node of 2.
Ravi, just one question. When we are storing next, in Python context, I'm asking, is it stored like in C? It stores the physical location of the, like we pass the address of that variable, right?
Right.
So in Python also same way, or it's just an?
It's the same way.
Okay.
It's just that the pointer concept is not there. Everything is handled by references. Okay. But that's the memory address. So reference is actually a memory address in Python. Okay. So everyone good till now. So when I'm using N1 here, I basically created a node of data 1 and it is not pointing to anything else. Similarly, when I have a node 2, it is basically a structure when the data is 2 and there is no next pointers. Okay, basically it is pointing to none. So this will create our individual nodes. Now we need to link them. That we need to have a single linked list that needs to connect all of these nodes, right? So we'll have another linked list class that will consist of a single thing, right? So if we talk of linked list as a whole, what is the only thing that we require?
Head pointer.
Sorry?
Head.
Yes, head, right? Because as a whole, we are seeing, when we are seeing from outside, it is just an entry point to the first node. So the linked list as a whole is a single entity, which internally combines all of this node, but from outside is just a single entry point. So when we are doing like this, we'll say that, okay, we'll call the self and we'll pass the head as well. So here we'll have only one attribute, that is head, and we'll set it from the constructor itself. So now we are almost done. So let's create 5 pointers now, or 5 nodes here. And we have this. Now we need to connect through them and we need to create a linked list out of them. So when we need to connect, we are saying that, okay, n1.next will be pointing to n2, n2.next will be pointing to n3, n3.next will be pointing to n4, n4.next will be pointing to n5. So basically, now our links are done, right? N1 is pointing to n2, n2 is pointing to n3, and so on. So our linked list is generated. But we don't have a single entity to reach n1 now, right? and that is our linked list. So what we'll do next is we'll try to create a linked list entity. And we'll assign, sorry. Okay, so that means when we are doing it here, we are making sure that we are creating a linked list. And what does the linked list expect? It expects a head. So we need to pass the head. And what is the head pointer here? So head is the first node, right? So we'll pass n1 here. That means we are done with our linked list. Okay, so linked list is single entity. We are enclosing all of them, and we are just representing the whole linked list by a single source of a single point of contact, you can say. That is a head node as of now. Okay, everyone clear till this point?
Just a Python specific question, means
Okay.
since the linked list will have the node, means is there a way, means like we can define node inside linked list, the class itself?
Yeah, we can define it inside.
So then means just asking, I don't know, do we get any benefit if we do like this or the other way around?
So it depends. So there are other complications we need to take off, like this is an internal structure. So language wise, I don't see any difference of memory and all, because when we're defining a class structure, the memory is not allocated, right? So when we're defining an object, that's when the memory is allocated. So I don't think it will be creating much of a difference. Otherwise, just implementation details are changing.
Okay, thank you.
Yeah. But I'm not very sure of internals. Maybe if they're internally storing it as a inner class, if the memory layout is a bit changing, then I need to check that.
No, I was correlating with C. Sorry for that, because means in C we put the node inside the linked list itself, right? And then put next and
yeah. In this also we can put, like if you consider the Java also, we also have the same structure. Like we can have the static nested class inside another classes, and it doesn't create difference. So it is a programming practice, what we can say. Okay, so if this external entity has some significance, then it should be kept as external. But if the node class here is only used by linked list, then there's no point of keeping it outside, right? So it is part of the linked list. So why it should exist as an independent entity? But for the sake of brevity, we are putting it outside. We're learning it for the first time. But if you wish, you can put it inside as well. Not an issue. Okay, so I think we have created our first linked list. Everyone else is clear?
Okay.
Yeah,
So the linked list, we are passing just the first node to the linked list. We are just passing, I mean, to the head pointer, we are just passing the location of the first node, right? And
right.
The line number 17, 18, 19, 20 are taking care of the rest of the list, right?
Right.
Okay.
Okay, so if you're very confused, I'll show you a diagram. So
Yeah.
we have N1 suppose as this, N2 as this. Yeah, want to say something?
Yeah, the linked list object that you have created of
Yes.
class linked list.
Okay. This is a linked list object.
Yeah, I'm clear.
So linked list has a single attribute, that is head. The rest are connected internally. So we don't need to take care of that. If we have the access to the first element, we have the access to the whole list unless we have some breaking in between. That will not happen for us because we are doing it manually. Yeah.
So we are creating like one class for node, one class for linked list, right?
Yes, exactly.
Right.
Okay, everyone clear?
Yes. Yeah.
So can we mention head inside init function?
Inside the node?
Yes.
No, actually the head is not part of a node, right? So head is an attribute of linked list. If you think of a design pattern, solid principles, right? So each function should have their own responsibility of what they're doing. So node doesn't have an attribute of head. So node is a single entity. So single entity has just a value and it's pointed to its next. So if we put head inside, there will be multiple problems that will happen, right? First, all the nodes will have a head now, which you don't want. We just want a single entity of head or a single instance of head.
Or Ravi, in place of calling the variable at 23 as linked list, we can call it as head, right?
We can, but
The left hand side means it's anyway the head pointing. It's a pointer to that node, right? We are not initializing. Just asking.
no.
Not
Actually,
So,
okay, that's a good question. I'll
So-
clarify.
so the linked list can also, you can treat it as an abstraction,
Yes.
right? So it can provide more than one operation. Right now, it just has the reference to the head, but it can do more things. So you are providing a layer of abstraction over the core thing.
No, means I am trying to correlate, like in C, we used to have a head and it will always store the address of the first, what you call the first node, right?
Right.
It
I got
was
it.
always global. The
I
reason
got
for that, it was accessible everywhere and means I don't have to pass it as a function, sorry, as a parameter.
Okay, so if you're saying about head, so we can do something like this.
Yeah. So another way, like in Python, can I make this as a global everywhere, like a constant? I can't change something like that. No.
We can. There are like everything you can do with every other programming languages, but this should not be recommended. Okay.
Okay. So ideally, I should have the linked list like you mentioned, and then head pointing to linked list dot head, right?
Yes, exactly. So linked
Okay,
list is an abstraction, as rightly said by Mantu. It's an abstraction. So it will have a multiple functionality. So when we're printing the linked list, it will have a print function. So when we call this linked list, so we'll call something like linked list dot print, right? So that's an attribute. So we are printing this whole list. When we are sorting it, so we'll call linked list dot sort, right? So similarly, what we're doing with the normal list structure, right? List dot sort or list dot length, whatever we are doing with the list, right? So similarly, we'll do the same things here as well. So think of it as an abstraction and think of that as
Okay.
provides multiple.
Just another thing, since you mentioned the length, means generally everywhere length is measured like len of the what you say the array, right?
Yeah. I just mistakenly mentioned that it should be like this.
Okay, no, I'm asking like in case of okay, we will come later, but if you can explain, like linked list will only have the head, right? To give the length, it has to traverse the everything and print the length. So when I am calling len of linked list, I should implement something which should tell it, right? The generic len function will not know, right? That my linked list.
Obviously. So even the print function, even the sort function, it's all custom. So when we're defining our own data structure, we should be defining our own functions, right?
No. That function definition will become like yeah, linked list dot length. There I can implement the way I want, but I mean, I'm not sure if I can.
Ravi, I think, yeah. So the Python inbuilt functions like print or len or sort, so those things works on the predefined structures, right? Not on the user defined structures.
Exactly, because if you think of why it works, that will make things clearer. So there must be something called a class list, right? So this list must have this length function like this, that is a hidden function, and there must be an exposed outer function that will be calling self dot underscore length, right? This would be the exact internal implementation, and the logic goes here. So it will not work obviously for linked list because there is no such thing. When we tell that, okay, I want the length, but it doesn't understand what the length is here. It understands in this context of list or queues or DQ, which have been implemented by programs like the custom modules, because they're already defined. When we are creating a list, it tries to create an instance of that class and it tries to call that method on that, right? So that should be expected.
Yeah.
Anyway, you're clear?
No, not.
Still not? Okay, you can stay back to the class, we'll discuss something. Okay.
Yeah.
Ravi, like one more question here. Not so. Suppose if we define a custom function inside linked list class, so when we create an object of the linked list class, using that object, like like way to access the function would be like the object name dot function name brackets, right?
Yes. Yes, yes.
With the argument if we have any. Okay.
Yes, yes. Perfect. All the things are the same. So we'll see about when we try to implement our first print function. So let's go to that. So we need to have a custom implementation of print. So when we call a print function, it should print the whole linked list as a single structure in whatever way we wish to. Okay. Suppose we want to implement our first print function wherein given a list, it will try to print that node 1 is here pointed to node 2 in this structure. Suppose we want to print it. Okay. And so on. So what should be done? Any ideas?
Yeah, like use a for loop and start from the head and keep incrementing the pointer
Right.
and until the node dot next is equal to null.
Right. So here
And
it should be a while loop ideally because we don't know the number of iterations. You can use a for loop and you can
yes,
break it inside. It's up to you, but I recommend it is while loop, going by the traditional methods. So not a compulsion. So everyone should be clear with this. So when we have this structure here, suppose this is the linked list and the last node is null, right? And this is something sort of this. So we started here with head. So what we'll do is we'll not never modify head. Okay. So this is the most important instruction. Never modify the head. So always try to create a new temporary variable that initially points to the head, right? So temporary points to head, then move the temporary to the next locations because with the help of this nodes next, you can access the next variable. With the help of this nodes next, you can access the next variable and so on. So what should be the stopping condition? The stopping condition is that when you reach here, that means when you are going, the next is not a valid number. So basically the next is a null. Okay. In that case, you need to stop. So always initialize a temporary variable, check the numbers, go and see. Okay. So if we code here, so we'll start with a temp equals to self.head. That is the first thing we got. While we'll say, okay, while temp is not equals to none, if it is none, we'll stop there. Otherwise, we'll continue, right? Then what will you do? We'll do print temp.value, sorry, temp.data. Because what is temp? Temp is pointing to the head node. So head is basically a node, right? So when we have access to temp, we have access to temp.data and temp.next as well. When we printed it, we do like this. We wanted to print it in an arrow format. And we move temp to temp.next. Because temp is pointing to the first node, accessing temp.next will point the temp to the next node in the picture. And it will go and we'll have the next till here. And we are done. So when we have this, now we can print this here and we can get the output perfectly.
So Ravi, like the print function, it's already like a Python predefined name. Yeah.
Okay. Thank you. We can do something like this. Perfect. Okay. It's not, why it is not taking this? I don't understand. It works in PyCharm. I don't know why this doesn't work.
And yeah, it does work.
Yeah. So, okay, then there is no point using this. We can directly do this. So it'll just point the number of elements and we'll have the contents of the linked list here.
Okay.
Okay, everyone clear? Any doubts? Okay, good. So now suppose we are printing, what do we say? Okay, let's not try to print. Let's try to insert an element at the last, okay? Or basically implement our custom append function. Okay.
Inserted last append.
Yes, we have this append function. Let's basically insert at the last, right?
Yeah.
So what do we need to do? So suppose we have this list that is already there. So there are some things that you need to take care of while solving linked list questions. Okay, so linked list questions might lead you to a number of reference error because you don't need, you might not be checking a lot many cases of this null. Okay, so suppose I'll give an example. This is a structure we have, and the last node is here. So suppose this is 1, this is 2, this is 3, this is 4, and this is 5. And suppose we want to insert another element that is 10. Okay, we want to insert at the last, and I want my new structure should be of this format: 3, 4, 5, and 10. Okay, I want something of this structure. So what I need to do is, how do I proceed? Any ideas? Just think it through. How we are given this structure, we are just to add that element. So how do we go there?
So
First,
basically,
we have to
Yeah.
we have to traverse through the list till we reach
Okay.
the end node, and then we have to point the end node head to the 10.
End node head or end node next?
What was that, Ravi?
End node's head or end node's next?
Uh,
There is
so
no
head
head for
is
this end node, right?
oh, so head is only for first list. That's what you are saying. What is difference between head and next?
Okay, got it. I got your question. Okay, so if you consider a single entity of node, so that single entity has two things. Okay, so when we talk of node class, so node has two things: only a data that it has the value, and the next pointer pointing to the next. Okay, when we consider this whole structure like the list, like the chain of the nodes, then we consider something as a linked list. That is an abstraction. Okay, in this there are multiple lists, multiple lists, not multiple nodes that are internally connected. But for here to identify what is the start point, so when you are taking, okay, you got this list, traverse me and find that, but we need to start it from somewhere, right? So for example, when I give the example of cinema hall, you know that your first friend knows the address of the second knows address of the third, but someone might know the address of first. Until how do we reach the first guy, right? If we are not able to reach our first guy, we'll not be able to find our whole crew. That's the problem, right? So someone needs to identify, and that is the responsibility of a class teacher, suppose. Okay, so class teacher will go and see, okay, this is the first guy I'll remember, and he will remember the next and next, and the chain goes on. So think of that class teacher as a linked list. So maybe that group of students, that class whole, right? Think of it not as a Python class, a normal um, teaching class. Okay, so the instructor maybe knows the address of first, and so on. You're getting a little idea?
Yes.
So every node will have a data and a next. Okay, but the linked list in general, in whole, will have the head.
Got it.
Sure?
Yes.
It should not be a big confusion, because if this is a confusion, it will mess up the later classes. If you're not very sure, tell me again, I'll explain it.
No, I got it. Like the whole linked list will have head, but
Yes.
each node will have only data and next point.
Correct. Okay, so we go to the last node and we change the next pointer of the last node to point to the new node, right? So we'll do something like this. Yeah. And this will have the last pointing to null. So when we start traversing from here, the new list will encompass our new element that is appended. Okay. So let's write something. So append. I hope append is not an internal function. Let's term it as my append. Okay. So here again, we'll not modify the list ever. Okay. So there are some people, what they do is they start with head while self.head not equals to none. They do like this: self.head equals to self.head.next. This is the biggest blunder, because at the end, when you try to access the head, you're pointing to the last element. And when you try to print it, you'll have only one element to print there. Okay. So you'll lose the whole context. You lose the first child. So everything is gone. So never do that. Always try to instantiate with a temporary variable while temp is not equals to none. So what should be the modified condition, or is the condition should be same? Janvi, you tell it.
It should be
While temp dot next.
Okay. And why is that?
because temp is the pointer which will be incrementing.
Exactly. So when we're printing, we don't mind when we land up to the null pointer, right? So actually at the end of the print function, our temp function will be pointing at this position. But we don't want to point to this position. We want to point to just the previous location. So what we do is we need to make sure that this next is not none. Okay. That means the node, the current node that we have dot next is not equal to none. We'll go till that. So that's our condition. And we'll have this. So here we don't have to print anything. We'll just move the pointers. Okay. And when we're done, after the end of while loop, we'll be at the last node, right? So my append will take a value. Okay. So here is the chance to create a new node. So we'll create a new node first with the value. And we need to make sure that temp dot next equals to the new node. So if we call the print before, and print will call the linked list dot append 100, and we'll call the linked list again dot print. It should be printing our new element over there, right? So I'll try to print a marker here. Okay. So if you see, we have 1, 2, 3, 4, 5 here, but when we print it after appending, the 100 is coming to us. Yeah.
Yes.
Yeah, Ravi, can you go a little up in the code? I want to understand one statement in class, linked list class.
Okay.
The line number 8, can you explain? I'm sorry, I didn't get it much.
Okay.
What
it's
is
the same thing, right? So
the left side self.head? That head is which variable is that?
okay.
Left side
so
head.
You are aware with Python, or you are coming from other languages?
Yeah, I am aware of Python. I mean,
okay. No problem.
Not very much.
Okay. What's you're comfortable with? Java?
C++.
Okay. So when we define a class in C++, what we do, I don't remember exactly, but suppose you define another class called my class here, right? So what you do is you define the variables here. So you define int A, int B, and int C, right? Then you define my class constructor here, and you instantiate the values over there, right?
Yeah, initialize the, yeah.
Yes. So when you're trying to access this here, replace this part in Python, remove this part. We don't need to do this. When we do self.a, self.b, self.c, it indirectly means that there is a variable A, B, and C as part of this class. Okay. That exactly this part is defining.
Okay, okay,
Okay.
okay, okay. So the right side head that you have written is the argument head in
Yes,
the
it
Python
is
code.
the assignment operator. Yes. Okay.
Okay, so basically head,
So it's the
the
same
left.
thing, right? So here also the node we are doing the data. So self.data equals to data. So when we are creating node of one here, so the one will be passed as data part. So self.data
Okay,
is the
I got my
at
confusion. So if in the line number 7, if instead of head, the argument head, if we write some other variable also, like some
okay, got it. First,
head pointer or first, something like that. So if you assign that same name here, got it, got it.
okay, cool. Yeah, clear.
Yeah, yeah.
Okay, so let's take a break of 5 minutes and we'll
Hello.
start.
Devi, can you
Yeah.
hear?
Sorry.
Yeah, I have a question. So each time we have to point to the next location, so we have to do it like n1 is equal n1 dot next is equal to n2, and then like that, right? So is it like, can we do it like in a loop, or like can we pass it onto the function or something like that, or like each time we define
Yes, you can. You can. So what you can do is you define a build function here. You pass a list, okay, from which you want to construct, and then what you'll do is you'll start with the head, okay. So you check the conditions. If the head is null, that means there is no elements. You need to call this append function regularly, right? List of. So what you can do is for I in range length of list, maybe name this as an input. We'll write input here. So you can call this append function here, and you'll pass input of I. That's done.
Okay.
You got?
Yeah.
So in this here, you need to add one more condition to check that if the temp or the head is null, okay? Because if the head is null, it'll try to assign null to the temp, right? In this function. Okay, we'll talk that after the break. So you got the general idea, right? What you're talking?
Yeah. Yeah.
Yeah, I'll explain this right after the break, and I'll tell you how it happens and what edge condition you need to handle over there.
Okay.
Okay, so we'll come back in 5 minutes. I'll start the timer. Okay, guys, let's continue. Okay. Yeah, Kavya, you're saying. Oh no, Kavya, I thought. Richa, you were asking something?
Yeah, so I was asking like how can we append like
Okay.
instead of appending it each time, can we do it through like a function, or like can we pass some argument through, like can we do it in through a function, like instead of doing it
Yes.
like each time? Yeah.
So what I propose, the build method should not be very ideal, okay? Because if you are passing through a list, then there is no use of creating a linked list through a list. So that is sort of a hacky way. So ideally, there should be something like, you should be passing one values at each time to construct a new object, okay?
Oh,
So
okay.
what you can do is, maybe you can call this append function at each iteration, okay? So
Okay.
you understood, right? So
Yeah.
suppose we had a list and you want to append a new number to this list. So what you do is you call new number to this append function every time. And by that, you'll be able to insert the elements at the last. But there is one catch we need to handle. That is, suppose, what if the initially we are a blank list, okay? There is nothing, and we want to append our first element, okay? So in that case, we need to modify our code a little bit. So we need to modify this here, that append function. If our temp equals to none, that means our list is empty, or linked list is empty. Okay. So you need to assign that temp equals to new node and return from here. Okay. So that way, what you can do is you just instantiate this here, and let's instantiate here, and let's comment this part. Let's comment this part as well. Linked list my append n2. Okay. Okay. So we are passing the. So what is append take? Append takes the value. We pass 2 here. Dot my append 3 here, and so on. So I'll just copy paste it. Okay. Oh, sorry. Okay, it's the same thing. Okay, so these are the special edge cases we need to handle. So while the initial list is done, so if you are appending to the last, what should be done over there, and so on. Okay, cool. So we'll move to our next part, that is deletion. Okay, so how do we delete our last element? Okay, anyone wants to discuss how do we delete our last element?
Like same way previously, right? We go till temp minus next is not null.
Okay.
So now we are at that node, and then.
And then.
Okay, no, we are pointing that we have to go to the previous one. We should be at the previous one, and that should point to the null.
Yes. So we need to go to the penultimate node this time, not this. And what we are doing is we need to modify this to point to null, right? So ideally, what we have done is delete this node, free this memory, and then reallocate the pointer. Otherwise, it will be a stale memory. So anyways, the garbage collector will take care of that. But if we are efficient enough, we should delete this. But as of now, as we're learning for the first time, I'm not doing those technicalities. So what we'll do is we'll just go to the penultimate node, the node before the last node, point the next to null. In that way, we'll lose this link. So when we lose this link here, there is no way we can access that. That means we have successfully deleted our last element. Everyone clear with this approach?
Yes.
Yeah.
Cool. So let's have another function. So if you observe, we are appending all of this function to this linked list class because these are part of the linked list. Node doesn't come into the picture. Okay, so node is just the internal of a linked list. So it will be delete last. Make a self, nothing else because the last is predetermined. So what we need to do is we'll need to go till temp dot. Okay, we initialize the temp. And while temp dot next not equals to none. Okay, so here there are a lot of things we need to handle. First, we need to handle that temp dot next is not none because none's next it'll throw an attribute error. I'll show you what we're doing, and what we'll do, we'll move forward, and then at this point we have the temp point into the penultimate node. We'll just make the next as none. It'll delete the last element. Okay, but there are several catches. We'll try to see that. So linked list dot delete last and linked list dot print. Okay. Marker. Oh, sorry. Okay, see, we have 5 things initially. Is this font visible or I need to increase this font? It's terminal font.
It's visible.
Okay, so initially if you see, I called my print function here right after appending. So it printed 5 elements, but when I call this delete last and I put a marker here, then I call my print function again. If you see, the last element is deleted. But suppose we have only 2 elements in this list. Okay, this algorithm will fail. Okay, should not be 2. Let's. Okay, so suppose the linked list has only 1 element or the linked list has no elements. So in this case, if you see here, the none type, this attribute error will come a lot of times while you code with linked list. Okay, so you need to take care of this when you are doing this. So how do we take care of this? There's a little trick. So when you're checking for this, the next dot next, make sure that you're checking for these 2 conditions. So when you're checking for temp.next.next, you should make sure that the temp is not none or the temp.next is not none. We should not go in that case, okay? But it needs to be handled in a specific case for deletion. Suppose there is only 1 element, right? So then what will happen is, we'll see here. So suppose there is, so let's consider there are 3 elements as of now. So 3 elements, that's fine. So we started our temp here. Temps.next.next not equals to none. Perfect. We'll move forward. Now temp is here. Temp.next.next is none. So we'll stop right here and we'll delete this. So what we'll do is we'll delete this and we'll point this to the last. That way we'll lose access and this element is got deleted. Now take the scenario of 2 elements, okay? So when we started this 2 elements, it'll be fine because temp.next.next is none. So it will not get inside the while loop. It'll just point this to the next. So this pointer will get deleted and this will work fine for 2 cases. So everything while submitting the code or showing it to the interviewer, always dry run this case once in your mind. Yeah. What happens when we have only single node or blank list? When we are single, the next is empty, right? So we cannot have dot next dot next. So in this case, you need to handle it a bit differently, that you need to make the head pointer to none. So this is a general statement. You don't need to check this, but for deletion or insertion, you need to handle it separately. If temp equals to none, you directly return because there is nothing to delete. Else if temp dot next equals to none, that means only single element, we'll modify self dot head equals to none and return. Okay, so this is the case of single element. This is no element. You can do temp here as well. Okay, in case of single element, we delete that and we return over there. Otherwise, we follow this approach. Okay. Obviously, you can write it in a better way, but I've just written it in a very crude format to make you understand. Any doubts, guys?
No.
Yeah, clear.
Okay, cool. So we run this, there'll be no problem at all. Even if the linked list is empty, we'll not be having any problem. Not a problem. Okay, so you should check these cases. Okay, so now we have inserted elements at the end and deleted elements at the end. Let's try for first and the middle. Okay, so how do we insert element at the first? Insert at first. How do we do?
Like new node, we create a new node and assign the head to the head of the new node, and new nodes next will be sorry. First new nodes next will be pointing to head, and head will store it in a temp variable, and new nodes new head will start pointing to the new node's head.
Perfect, got it. Okay, so I'll explain once again. So when we have this, initially we had head pointing to here. Okay, now we try to create a new node at the beginning. Okay, so what we need to do is we are changing the head pointer from here to here. But if we do it this way, then we lost the access, right? We lost the access to this first pointer here. So that's why what we need to do is we need to keep the head pointer intact for the first time. This is a new node, okay? So what we'll do is, we'll try to point the new nodes next to the head. That way we'll create a chain like this. Okay. And then we have the access. Now we can take up this head from here and can point to this. So this becomes head pointing to the new node here. And the new node is pointing to the old list of nodes. Everyone clear?
Yeah.
Cool. So I'll try to write one more example and the rest will be pretty easy. So we have insert first. So we'll have a self and we'll take a node value. Sorry. Okay. So what we'll do is we'll create a new node first. right? Then we need to check what is the head now, if there is any element present or not. If temp equals to none, that means there is no element there. We need to point the self dot head equals to the new node here, and we return. Else, what we need to do is we make the new nodes dot next equals to the head self dot head now points to the new node. Okay, make sure you understand the ordering, why we are doing this. Otherwise, if someone is saying, okay, we'll first make the self dot head to new node, then you lost the access to the old structure, right? You cannot do this new node dot next dot self dot head because self dot head is pointing to you now. So the order is important and you need to understand clearly this. Okay, everyone good?
Yeah.
Okay, so let's move on to the next. So now it remains, so we have covered insert, at beginning, at end, delete, at end and beginning, right? I think both of them. Delete last. Okay, we have not covered the delete first. Okay, so delete first, let's discuss what should be done. What should be done in the case of delete first? It's pretty easy, one line code. Throw in ideas, guys.
Ravi, is there any built-in function for LinkedIn that we can use directly?
No, as of now, there is no, but there is a DQ implementation like double-ended queues, which internally uses linked list. We can use that, but what you can do is you can create a whole, all of these functions, right? The delete first, delete beginning, delete at any position, and use that as a library, import that file in any part you want to use, and do that.
So to delete the first node, we have to change the head to the next point to the next node.
Okay, and how do we do that? Self.head equals to
head dot next.
Right. So always write self.head dot next. Okay. So because the head is part of this linked list object, we don't have an independent existence of head. So self.head dot next will do our deletion. Perfect. So now there remains two things, that is insert at any position and delete at any position. That will be a part of assignment. Think through, be easier. What you will do is you will be given a particular position to insert the element. Okay, so suppose K is there and you want to insert there. So first you need to validate whether that length is that of K. If not, that's pretty simple. You just insert it at last. Otherwise, if it is a blank, you need to insert it at first, and otherwise you just need to go to a particular position and insert that element. And similarly goes for deletion. So these two are part of assignment. I'll upload that soon. Okay, we'll be able to do it, guys, or you need some help. Try it once. Maybe it'll be easier to write the code now.
Yeah, we'll try. Ravi, like to extend Janvi's question, like so like when we get a question based on linked list, so there like we get a question, some like we get a question related to implementation of linked list, or like I mean like so here we are implementing linked list using base like predefined structures,
right?
But like in interview, do we get an implementation of linked list kind of questions, or directly we can like we have question where we are given a linked list, and or what I'm trying to ask is like
yeah, I got your question. So
yeah,
basically
directly use linked list and solve a different problem like that.
Right. So it depends on the platform they're using. So suppose if they're using platforms like HackerRank and LeetCode for your first round, then
Mhm.
you will get mostly a function completion. Okay. So a linked list will be there and you need to return the updated linked list. So there'll be a function. So they'll be taking a linked list and you'll be returning a linked list. So their code will handle the initiation and the validations. Okay.
Okay,
So
so
suppose,
we'll be just given the object of the linked list
right.
and okay.
And but suppose if your test is happening on CoCubes, like Microsoft takes it and CoCubes. So if Microsoft takes it, so there is no concept of function completion. You need to write the whole linked list structure and implement the functionality. Okay. So it depends. But ideally, mostly you'll get function completion wherein you take the linked list object, you manipulate the linked list object, return the linked list object. That's all.
Okay, and if the if the round is face-to-face round,
Face-to-face round,
the
mostly they will never implement, they'll never try to implement this. They'll try to implement a function because it is always a time crunch, right? So there'll be 45 minutes to 1 hour around. So if they go on to let you build a linked list on your own, it'll take 30 minutes of your time. So the next 15 minutes or so will not be very sufficient. So as per my experiences, I have just gotten questions on function completion as well in the interviews.
okay, okay,
Yeah.
thank you.
Okay. I think, yeah.
Just curious, the deletion you did right now.
Okay.
So you're just moving the linked list, which is outer layer, pointer from the first element to the next element, right? The second element.
Right.
But you also need to decouple the first element's next reference, right? To the
We don't have an
otherwise,
access to first element right now, right?
no, but that element has a reference of next, right?
Exactly. So that's what I told at the start. So you need to ideally do that for every case we need to do, right? So you need to delete that node, you need to dereference that reference, and
Yeah,
then
dereference that. So then it becomes a complete deletion, right? Okay.
yes. So that we should do. But as of now, we're starting for the first time. So I'm thinking that garbage collector should be taking care of that. But ideally we should do. Yes. So if I would consider like after 5 classes or 10 classes from now, I should expect that while you implement this functionality of position, you should consider that freeing of space and freeing of the references as well. Okay. Okay, cool, I think. So now let's move to some interesting problems on linked lists. So we'll see a very standard problem that is generally asked, that is cycle detection. Okay, so how do we detect a cycle in a linked list? So there are two things. So this is the first linked list. And this is second case. Okay. So these two cases come generally in case of cycle detection. But the first one is not a valid case for us because that is a circular linked list. We are now studying single linked list. So we'll ignore that case for now because that is not a part of this question. If you try to solve it, you'll never be able to solve it with the algorithm that will be covered now. So we'll be only dealing with the second type of cases. So to clear the first type of cases, we'll study when we discuss circular linked list in the next, after we learn this deletion. Okay. So only we are considering this scenario where the cycle is not pointing to the head node. Okay. The cycle is pointing to some other intermediary node over there. Cool. So now let's think of what can be done in case of cycle detection in linked list. And how do we ideally get to know that there is a cycle even? Any ideas?
Yeah, like use 2 pointers, like
Okay.
slow moving pointer and fast moving pointer.
Okay. And why
So
that will work?
yeah, it works because um, at one point of time, like fast pointer will overlap the slow pointer. So
Okay.
the point where it overlaps, we like basically there will be a node where both the pointers will start pointing at a particular time.
Correct.
So that
So if
place
others
we
are
get.
not able to get there, so think of this as a stadium. Okay. So given a stadium, you are running and one of your friend is running as well. So you are running a bit slow and your friend is running a bit fast. So it will happen that whenever you start, whatever you start with, no matter, at least once, if you're running for the whole day or if you're or thinking for running for infinity, then at least once you will override, right? However fast or however slow you're going, at least once you'll meet. Everyone getting this generalization? So you are rotating in a slower speed, your friend is rotating at a faster speed. At certain point, you will meet each other. Okay? Everybody
It's
is
just like
okay?
clock hands, wall clock
Exactly,
hands.
exactly. The hour hand and second hand or minute hand and second hand. So whatever position they are in one revolution of either one of them, it will try to meet perfectly, right? So that's the concept we'll be using. So we have learned about two-pointer technique in arrays. So there is a two-pointer technique in linked list. So that is termed as fast and slow pointer. So we'll be using an algorithm called Floyd's cycle detection algorithm. Okay. So this is Floyd's cycle detection algorithm proposed by Floyd. So what it says is that it just says the exact same thing that we have already discussed. So we start at same point and we start with the slow and fast pointers. Okay. So we start one with green that is a bit slower and we start one red that is a bit faster. Floyd says keep moving the green pointer by 1 places and keep moving the red pointer by 2 places. Okay. If at any point they meet during the journey, then we have a cycle. So let's see. In the next iteration, what happens? So green goes to the next here, red jumps 2 positions. So red is here. Now in the next iteration, green goes here, red goes here to here. Okay, everyone clear till now?
Yeah.
Now the green moves here, the red moves here and here. Okay. Now the interesting point. Green moves to next position, red moves from here to 1 and 2. Now they both intersect at this position. Okay. So that means when we follow this algorithm at one point in this, if there is a loop, we'll meet. And provided this condition works when we have the last is not null, okay? Because if the last is null, obviously that will terminate. So we are assuming that there is a cycle in here, and that's where we'll detect through this algorithm. So here is the point when we'll be able to detect or find the cycle. Everyone got this idea? This is very simple.
Yes.
Okay, so now we have found the cycle. Now, what is the next task? The next task would be to remove all of the cycle. So what do we expect to remove? So when we expect to remove, then that means we want this link to be somehow broken, right? So we want this link to be pointing to the null pointer. So that means we'll have our single linked list like this. Okay, so we'll have our circular or cyclical linked list as a linear one now. That's the next goal. Okay. For that, this algorithm proposes a next solution as well to that problem. So our whole challenge is, if you think of this, what is our challenge? The challenge is that we don't know at what point it will meet, right? We're never sure that it will meet at the first or at the end. So if they would have always met at this position, then we would have easily terminated that, right? So we have like made the next of this pointer here or this node here as none. That'll do. But the problem here we are facing is that we're never sure at what position they're meeting. They can meet at here, they can meet at here, they can meet at here, whatever. So we need to formalize a formula to reach over there. Okay. So that is a very interesting calculation. So suppose following the previous approach, we met here. Okay. Now, what we'll do, let's form some equations. So this is slow and this is fast. That is the fast pointer that we're talking of. So when we have this, what do you think should be equal for both of the slow and fast pointers? Or what should be compared or what could be compared for this?
The distance that they cover.
Right, the distance, right? Because the slow is moving one place forward and the fast is moving two places forward. So obviously the distance covered by the slow pointer, suppose if that is d, the fast pointer will have covered twice the distance. Everyone clear?
Yeah.
So let's consider the linear length as L now, okay? And the circular circumference as X, okay? You clear till now? So this is just the assumption we are doing on the linked list. So the linear length that is before the start of this loop is denoted by the letter L that defines that, okay, this is the length. So this means here the L should be 3, okay? And here the X should be 4. So let's treat it in terms of variables. We'll be getting to a formula. So when we have got L and X here, what is the distance covered by the slow pointer? So both of them will have covered the same linear length, right? Because they are rotating in this part. Like in the circular part, there will be multiple rotations, but the linear distance that is traveled by both of this pointer will be same. Do you agree?
Till the meeting point, right?
Not the meeting point, right? Suppose the linear length is that, then after the linear
Okay.
length,
Yes.
they will get around this part, right?
Yeah, correct. So L will be traveled by
So both of them will have traversed the maximum and yes, correct. Okay, everyone agreeing, or anyone has any questions here? Understand bit by bit of this part now.
Can you repeat the second point? What is how linear would be same?
So how the path of the slow pointer will start from this position here, and it will go and it will continue at this position, right?
Yes.
And the red one will start from here, it will go and continue in this loop.
Yep.
So the linear distance traveled by both of them is equal to L, right? Agreeing?
Correct. Yeah. Before getting into circular loop.
Yes, right. So now suppose to meet this, the slow pointer takes n1 revolutions to meet this, because we don't know, the revolutions will be different. The number of revolutions to meet this point taken by the slow is n1. The number of revolutions took by n2 or the fast pointer is n2, okay? So what we can say is the slow pointer has traveled the distance of L plus n1 into x, right? And we mark this something as the length of the intersection from the point of beginning of the loop. Okay, let's term this as y. So L1 plus N1 x plus y should be the total distance traveled by the slope pointer. Any questions?
So it might be a silly question, but like the like what are the chances that both of them would have taken more than one like the first pointer will obviously it would have taken at least more than one like revolutions, but what are the chances that
Okay.
the slow pointer will also uh, take more than one revolutions to get a intersection?
Not even one. We can take the N2 as 0 as well. Okay. But the generalization will be that, right? So if the N revolutions are there, we are just comparing the total distance.
No, what I'm trying to ask is, will n1 be more than I mean, will it be zero more than zero?
It can be 0 even. It depends on the condition. So if the condition is like there is one loop over there, like if there's a bigger loop, then N1 might be 1. If there's a very small loop, like there is only one edge over which it turns back, then we can say that it
Okay,
will,
okay, I got it. Yeah, it depends on the number of nodes that are there in the cycle.
yes.
Okay.
Yeah. So the distance covered by the slope pointer is this. The distance covered by the fast pointer is L plus N2x plus y.
X plus Y. Yeah.
Everyone clear? Anyone has any doubts? Please say it out. It's very important.
And n1 can never be equal to n2, right?
Yeah, it will never be equal to N2.
And y is the distance from like the meeting point distance, right?
Yeah,
Y.
it is from the starting point to reaching point. Because in this part, this is not complete revolution is happening, right? So it can happen that there is some intermediate node wherein these both meet.
Okay.
Yeah, so that will be the same because when they're meeting, the distance from the starting to that position will be y for both of them. Agree?
Can't visualize it in my head, but I'll just assume it and go ahead.
No. Okay, I'll explain one second. No problem. So suppose this is the starting point of the loop and the both of them met at this point. Okay. So this part here, we are treating it as y. So if you observe this, this is not a part of a revolution, right? For any of the slow or fast pointers. So this is an extra additional part. We can think of it as an offset. Right? Okay, maybe I'll give an example. So let's take the example of a clock, okay? So clock started at 12. So both of the needles, the hour hand and the minute hand, both started at 12. And suppose they both met at 4. Okay. So the hour hand must have taken n number of revolutions, but the distance traveled by the hour hand will be n times, suppose each is a unit. Okay. Each is a unit. So we can say that n1 into 12. So each is a unit distance, what I'm saying, plus if they're meeting at 4, then I'll add this to 4. That's the distance traveled by the hour hand.
Yep.
Yeah. So if the other hand we're talking of, it will be covering the distance 12 of n2 plus 4. Only the revolutions will be different because it will.
Yeah, they're proceeding at a different pace, right? So yeah.
So the meeting point will be same. So the number of revolutions will be different. So the total distance will be different. The extra offset for both of them at the end of the loop will be having a same number here.
Okay. Yeah, because the base point is
Right?
same. Yeah. Yeah. Okay.
Exactly. So it's the same thing, just we have added the linear distance. So it's linear L plus N1x plus Y, and it is L plus N2x plus Y. Okay. Everyone?
Yep, clear now.
Yeah.
Okay. So now we know that this distance equals to this distance now, because the distance traveled by the fast pointer will be equal to the twice the distance traveled by the slow pointer. So we can write twice the distance of small d equals to the distance by the fastest one. This is also critical.
Yeah.
Okay. So what we'll do is we'll take 2L plus 2N1x plus 2Y equals to L plus N2x plus Y. So what we are finding, okay, X, okay, I'll remove this, but I'll draw the diagram here again. Can I draw that? Okay. Okay. So what we can do is we'll pull the L to one side. Let's try that. So 2L L, so L comes here plus equals to, let's bring Y over there. So it's minus Y plus, what do you say? N2 minus 2N1 X, right? L is here, Y was there, N2 minus 2N1 X. Okay, so we have got this now. What next? What can we deduce from here? Okay. So we can take Y to that. L plus Y equals to, okay, so this is suppose the relation that we got. Okay. Now the important point, we want to make a deductions in here. Okay. So suppose we know that N1 and N2 will be integers. Everyone agree?
Yeah.
Just be for some minutes, guys. It'll be very easy. Okay. We are mostly done. So N1 and N2 will be an integer. Okay. So we can say that this number here will be an integer.
Yes.
Yep.
Any number, positive, negative, doesn't matter, but it will be an integer, right?
Yes.
So I can write this as kx. This can be L plus Y now. Okay. Everyone clear till this point?
Yeah.
Okay. So that means we have a relation L plus Y equals to kx. Okay. I'll make some space here. It will be easier to understand. I'll remove the mess. This one, this one, this one is L, this one is Y. Okay, so now our whole goal is to find the starting point. Now what we'll do is just forget the formula. Let's just figure out, for some reason we know that we got our point of intersection at this position. Okay, now we started from here, another case. Okay, so what will we do? We'll traverse L from both of these ends, from here and from here. That is, now there is no slow and fast. Now there is only P1 and P2. Okay, both are moving at the same pace, that is 1 and 1. So suppose both are moving L distance. Okay, so let's denote this as P1 here. Let's denote this as P2 here. Okay. So both traverse L distance. So where will be P1 after L distance?
At the starting of the cycle point.
Here, right?
Yeah.
And where will be P2? It will be at Y plus L. Guys.
Yes.
P2 will be at 2L, but not sure.
Sorry?
P2 will be at 2L, right?
No, P2 is at Y, no. So P2 we didn't change. So this is the point of intersection.
Oh.
So
no.
It travels
So when
P1. Yeah.
Ravi, so like if we are incrementing P1, what are we doing with the P2?
So we are incrementing L distance with P2 as well. Now both are moving with the same speed.
So in the forward direction or backward direction, P2?
Forward. We don't have a backward direction, obviously, right? Because it's a single linked list.
Yeah. Yes. Sorry.
Okay.
So P1 moves L distance. So
how much P2 will move?
P2 will moves L distance. Y plus L.
So the overall position for P2 will be Y plus L. And the overall position for P1 will be L, right? Everyone clear or you have a doubt?
No, it's clear.
Okay. So from the formula previously, we know that L plus Y equals to Kx. That means what? That means when we add L to Y, we are having an integral number of X. That means where they should meet. X, what was X? X was the length of the circumference, right? Or the whole circumference is the length of the circle. That means when we're saying Y plus L equals to some integer into X, that means it can be 1x, 2x, minus 1x, minus 2x, depends, right? So if I start at the 0 position of X, where should I meet?
0 again.
It should be 0, right?
Yeah.
Because we are making an equal revolution, either 1 or 2 or 3. It is an integral. Or minus 1, that means we are moving a place backward. So don't think of minus. Think of that as we are taking complete revolution around the circle. That means we will be meeting at the starting point. Everyone clear or you have doubts?
Yeah, so L plus Y equal to Kx. So L plus Y is not the like point where revolution like cycle starts. It's the point where they meet, right?
So Y is the point they meet, right?
Y or L plus Y?
No. In terms of this point only, from this point, this length is Y, no? So obviously L plus Y, but in terms of the circle, I'll come again. So this is the linked list. Okay. So now this is Y, this length. This is the starting point of the P2. This is the starting point of P1 here. Both are moving L. So both are moving L. So P1 will be 100% on this position, right? Everyone is agreeing because that's the length of the linear chain. For P2, it was at position Y. When we added that to L, we had a relation that Kx. That means X was the circumference length. Right? So if we add Y to L, that means we'll take a full revolution. Kx, what K means? K will be 1 or 2 or 3 or 4 or minus 1, minus 2, minus 3, minus 4, right?
Yes.
So that means Y plus L, when we add, we will complete some number of revolutions, and where will be our final position when we say that a clock complete a revolution, it will go till its starting point, right? So what was the starting point of the circle?
Loop. That's where loop started.
Exactly. So here we are able to make some position to point both of these pointers to this first point, right? And this is a foolproof solution now. So we have devised a logic wherein following this approach, always and always will get the first point of this loop. Any doubts? This is a little bit tricky. So even if you have silly doubts, please let me know.
So just a quick question. I got this point. I just want to understand a bit more about where you have derived. You multiplied it with 2, right?
Yeah.
In the derivation part. So I'm like a bit unclear in that part. Like
Okay.
why?
Oh, I removed that. Oh no, here it is. Yeah.
Yeah.
So, okay. So this was the left, this was the distance traveled by the slow pointer, right?
Yes.
And this was the distance traveled by the fast pointer.
Correct. Yeah.
How do they do both relate? What is the distance relationship? The distance relationship is the fast pointer should have traveled twice the distance of the slow pointer, right?
Okay. Yes.
That's what.
Okay. Yeah.
The next step.
Yeah. Now I got it. Yeah.
Okay.
Yeah. Okay.
Cool.
Yeah, I got it. Thank you.
Cool. How about this? Any questions?
Yeah, Ravi, like I need a bit
Janvi,
more clarity here. Like y
Okay.
plus L equal to kx. So y plus L is the point where they meet, right? So
Okay.
I
So
mean,
y
how
plus
do we
okay, I
come
got
to
it.
know that the like the point where loop starts? How do we like conclude? Because y plus L distance is the point where they meet, not the point where the loop starts.
Perfect. Yeah, great question. So y plus L, who is traveling y plus L now? Not this one, right? If this would have traveled y plus L, then this would be meeting at this point. But who is traveling y plus L?
Slow pointer.
There is no slow pointer in the second phase. So this is the second phase where we have found out our
Okay.
meeting point. So this y plus L is traversed by P2. And why it is y plus L? Because it has y from the point of intersection, from the start of the loop. And both are moving L distance now. So it is the overall final position for pointer 2. You got? Or you still not clear? Okay, see. This is the case, right? So this is the starting of the loop.
So
And
how
suppose
did
this
P2 reached a y plus L distance?
no, you are getting confused. So now the phase 1, while in phase 1, we decided that it was a meeting point, right?
Yes.
And that's what is the length? That is y from the start of this loop.
Right. Yeah.
And then we resetted P2 here and P1 here. That is phase 2 now. This begins phase 2.
From the phase 1, we got a intersection point and we kept the P2 at there, and
Right.
P1 we moved back to first point.
Exactly.
Beginning
Now
of
both
the
of them move L length. So if P1 moves L length, it will come here.
Yes.
P2 will move L length. So it was at Y. So Y plus L, as we know that it is a factor of K.
Okay. Yeah.
That means it will be a complete revolution. So it will be also here as well.
Okay. Yeah. From the derivation, we get to know that if they both move L distance, one like P2 at the intersection and P1 at the beginning. If they both move L distance, they will definitely meet at the beginning of the loop.
Exactly. Because we are always concerned about beginning of the loop. If we are able to find the beginning of the loop, there is a child's play, right? We'll just go this one here. That's the whole concern.
Yeah, I mean, I got both the phases isolated, but I was not able to relate both of them. So now I was able to connect.
Others, what about you? All clear?
Yeah.
Okay. I should not expect this while writing the code tomorrow. Okay. Like I have this doubt at this point. Please, if you have doubt, tell me right now. I'll not again touch this derivation in tomorrow's class. Okay. I think everyone is good.
Just one more question, David.
Yeah,
so we
sure.
took it like two distance of the point at phase one. We took the distance between pointer one and pointer two as like two, right? Can we, is it like two always, or like we need to like we have to like guess on, or like it's then anyway like which might be the two or like three? If it is three, will they meet, or like is there any anything related to that?
So this algorithm that is very specific to two. If three might work, might not work. I need to check whether there is any algorithm around that. But
sorry, what's the question? Like 3 pointers or
no? She's saying we are moving two places forward. What if we may move 3 places forward? Will this algorithm still work?
Okay, fast pointer moving 3 places forward.
Yes. So ideally, I think it should, but we'll again have to derive. So let's derive that 3 into distance equals to distance. I don't think it will work. Okay, let's try to figure it out. Okay, I'll create some spaces here. So it will be 3 of L plus N1x plus Y equals to L plus N2x plus Y. Okay. It is 3L plus 3N1x plus Y equals to L plus N2x plus Y. So can we figure out something from here? That is 2L plus, okay, so it will be 3y, so it will be 2L plus 2y equals to N2 minus 3N1x. Yeah, we have to move now twice the distance of L plus Y. Okay, now you got the problem.
Yeah.
So in this case, we already have the position of Y, right? So we don't know the starting point. How will we move to Y over there?
Okay.
You got the problem, right?
Yeah.
No,
So
I didn't get the last point. Like if it is 2L plus Y that we have to move both the pointers, why will it not?
So here it was Y, right?
Yeah.
Okay. So we don't know the Y's value because we don't know the starting point till now, right?
We also don't know L value, right?
Sorry?
We also don't know L value. That means if at all.
So L value, okay. So we'll be able to know while we're coding. So you'll be able to figure it out tomorrow. But for now, let's think that we don't have Y value, right?
Yeah.
So if we have to move another Y distance, how much length we have to cover? We don't know that. So that's again a problematic situation for us. Got it, Rija?
Yeah. Yeah. I'll go through it one more time.
Yeah, just go through it one more time. Go through the derivation part. You'll be very clear about why we are not able to do that.
Okay. So this one work with two. So we always take first algorithm.
Yes. You'll always take 2 as of now. Okay. So we'll continue it from this point in tomorrow's class, and we'll see the code, how it works, and we'll see some problems on linked list tomorrow. Okay.
Ravi, like, sorry to interrupt. So if we consider half of this question, like just to find the cyclicity, if
Yeah.
the loop exists or not.
Mhm.
So for that case, if the pointers are moving faster than twice the distance, like 3x,
That's
like,
not a problem.
so for that it should work, right?
Yeah. It should work.
Only finding the intersection, I mean, the start of the loop, or basically breaking the loop will be
Right.
problem. Okay. Okay. Sure.
Yeah. Then. So
Tomorrow we are going to discuss like linked list only.
yeah,
Or
we'll be covering linked list as well. So we started. So I think it'll take 1 or 2 classes more. So we'll see some problems. If we are able to figure it out, we'll see some